Hello everyone, welcome to this video. In this video, we'll be solving this question which states that prove if an abelian group has more than 3 elements of order 2, then it would have at least 7 elements of order 2, correct? And this is the first question. So let's first look at this question, right? So here we consider G to be an abelian group, right? In this group, if we take any two distinct elements A or B, right, which are having order 2, then according to the definition A square would be E and B square would also be equal to E, right? So what would be the order of their composition? It would be AB, right? And its order is also 2. How? If you take its square, so that means you are writing it like this: AB multiplied together with AB. Now you can use the associativity to combine these two elements and shift the brackets, right? Here you can use the property of commutativity, that because we are given the group G to be an abelian group, so you can write BA as AB. So you can write it like this, right? Now A into A becomes A square, B into B becomes B square, A square is E, B square is also E, so E into E is E. So therefore the order of AB is equal to 2 in this particular case, right? Moreover, this element AB is not equal to A and it is not equal to B, right? So it is distinct element from A and B. So that means in total we have one element as A, another as B, another as AB, which are having order 2. So the order in each of these three cases is equal to 2, right? Now we are given that G has more than 3 elements of order 2. So we have to prove that it at least has 7 elements of order 2. So we already have 3 elements with us. One is A, another is B, another is AB, which are having order 2. Now let us assume some fourth element C, which is having order 2, right? In that case, you can also find elements AC, A multiply together with C, B multiply together with C, and AB multiply together with C. They all would also have an order equal to 2, right? This shows that there are at least 7 elements. 3 of them are the previous one, C, which we have now taken, and AC, BC and ABC as composed with the previous elements. So they all would also have the order 2 in G. So therefore in total, if we take more than 3 elements, we had initially taken A, B and C elements as the 3 elements. If we take more elements, we would have more number of elements which are having order 2 in this particular case. Hence we would say if G has more than 3 elements of order 2, then it would have at least 7 elements of order 2, right? This is what we wanted to prove in the first part here. Next question says find an example that shows that this is not true for non-abelian groups. So for when you think about non-abelian groups, dihedral groups, they come into our mind foremost, right? They are our favorites. So therefore for this thing is not true for non-abelian group. This is very easily could be seen through the dihedral group, which shows the symmetries of a square D4. You know, there are 8 elements present within this group. In this group, the order, if you see the Cayley table, you can see that the square of only 5 elements are 180, H, V, D and D dash. They becomes R0, which is the identity of the group, right? So therefore we only have 5 elements here which are having order 2. However, we said that if for a abelian group, if remove this word, now the definition becomes if a group has more than 3 elements of order 2, then it has at least 7 elements of order 2. Here there are 5 elements of order 2, right, which are obviously more than 3. However, we do not have at least 7 elements of order 2 because there are exactly 5 elements present within this. Hence this thing is not true when we remove the condition of commutativity. That means this thing is not true for non-abelian groups in general. So I hope you understood this question well. Well, that is it for this video. Thank you for watching.